Hello and welcome to the photoelectric effect. This is a simulation of the photoelectric effect. We have a lamp which is emitting light. We can control the intensity of the light and we can control the wavelength of the light that's being emitted. The light is shining onto a metal plate and we can select which type of metal from this drop-down box. We are using zinc. That metal plate is connected to an electrode here, and that electrode is connected to a battery. Now this battery has 0 voltage, so at the moment it is behaving like a wire. It's not doing anything. There's no voltage in this circuit. The other end of that wire is connected to another electrode, and you'll notice that there is no current flowing. This experiment showed very, very interesting results that could not be explained by the wave theory of light. Now, the wave theory of light tells us that the lamp is emitting waves, continuous waves, that are travelling across space and landing on the metal plate. If we wait long enough, then lots and lots of energy is going to be delivered to the plate. So if the electrons inside this metal are going to collect enough energy to be released from the plate, then according to the wave theory of light, all we have to do is wait. It's a little bit like connecting a phone charger and waiting for your phone to be fully charged. You just have to wait. If we increase the intensity of the light, then we should have to wait less time, in the sense that a more powerful phone charger will charge your phone faster. But it was observed that at some frequencies, some wavelengths of light, the phone never gets charged. Electrons never get released, even though we are waiting and waiting and waiting, and more energy is being delivered to those electrons. It just wasn't working. And this is one of those wavelengths. Nothing is happening. If we increase the intensity of the light, that has no effect, which is unusual. We would expect that a more powerful light, a brighter light, would deliver more energy to the electrons on the metal plate, and those electrons should eventually be charged up enough, with enough energy, to release. And we would expect them to be released from the surface and travel across the gap to the other electrode, where they make a current in the wire. It was noticed that some types of light this worked, and some types of light it did not work. This wavelength here, 690 nanometers, is a wavelength that does not work. But if we change to a different type of light, then we can get this phenomenon to occur. For example, with UV light. The UV light is delivering energy to the metal plate, and the electrons are absorbing that energy, and they have enough to be released from the surface, and they travel across the gap, hit the other electrode, and create a current in the wire. We did not understand why it would work for some types of light and not others. You can see here that no electrons are being released. And it came down to our understanding of the nature of light. If we study light as being a continuous wave charging up the surface, that doesn't work. It does not explain why we do not get results with one type of light, but we do get results with another type. Instead, we needed to change our understanding about the nature of light. We needed to understand that light is composed of photons. So it is not a continuous wave of light that's arriving at the plate. It's a series of particles called photons. And irrespective of the intensity of the light, the brightness of the light, each one of these photons has the same properties as the others. So we can have a lot of those photons arriving or very few. And each one of those photons is delivering the same amount of energy to the plate. And each one of the electrons in the plate is absorbing one photon. So it now becomes important to understand the energy in each one of these photons. If the energy of one photon is enough to release the electron, then the electron will be released. If the photons are too weak, then that energy will be dissipated into the metal plate and the electron will stay where it is. So some colours of light have enough energy in their photons to release an electron, and some do not. Here is an example where these photons are not energetic enough to release an electron. But if we change to a different colour of light, then we can see that these photons do have enough energy each to release one electron. The light is emitting individual photons, and each one of these has energy. If that photon has enough energy to release an electron, the electron will absorb it and it will be released. These low energy photons arrive at the plate, they are absorbed by an electron, but that electron cannot escape with this low level of energy. The energy that is absorbed by the electron gets dissipated into the surrounding material. Some wavelengths work, some do not. If we gradually increase the energy of the photons, then we notice that there is a certain value at which suddenly we will get released electrons. These released electrons are called photoelectrons. Photo for light. There we have it. So this is approximately the threshold frequency or threshold wavelength at which zinc will release photoelectrons. The amount of energy that's needed for one electron to be released is known as the work function. And it turns out that different materials have different work functions. We are currently at the threshold wavelength or threshold frequency for zinc. If I change to a different material, for example, copper, that will have a different work function. Or platinum. Notice here that platinum, we don't have any photoelectrons being released. Presumably this wavelength is not enough. So if I increase the energy of the light, we will find the threshold at which photoelectrons will be released for platinum. Notice that these photoelectrons are being emitted with different amounts of energy. Some of them are moving very quickly and some of them are moving very slowly. This is because they're coming from different parts of the metal. The ones that are moving very quickly were at the very surface of the metal, and so they needed only a little bit of energy to escape. That is the work function. The electrons that are deeper inside the metal, they need to work their way through to the surface and then they can escape. So the work function is the minimum energy required to escape for an electron that is right on the surface, and those are the ones that you can see moving very quickly indeed. The slower electrons are the ones that have had to use the energy that they absorb to work their way through the metal and then escape from the surface. So when we are talking about the energy of the photoelectrons, it's more useful to think about the ones on the surface, because the ones on the surface only needed to absorb that minimum amount of energy, which is called the work function, and they will have the maximum energy of all the other photoelectrons. We call this the maximum kinetic energy of the photoelectrons. There are several equations that you will need to understand in order to talk about this experiment, and we're going to go through those next. We're now going to define some of these terms. We've got 3 screenshots here, and each one shows different types of results that we get with the photoelectric effect experiment. We have light arriving at the metal plate and no photoelectrons being emitted. We have light arriving at the plate where we only get the very surface photoelectrons being emitted, so that is at the threshold wavelength or threshold frequency. And we have the situation where we have a range of different velocities of photoelectrons traveling away from the plate. So this is where there's lots of energy being delivered, and electrons that are not just at the surface but also deep down in the metal are capable of being released. So the first thing that we need to understand is how is the energy of a photon, these particles here, how is that defined? The energy of a photon is Planck's constant multiplied by the frequency of that photon. So that's the colour of the light, whether it's red or green or blue or maybe infrared, ultraviolet, gamma rays, all different types of light. The frequency is what helps us to understand the energy. The higher the frequency, the higher the energy. Planck's constant is literally that. It is a constant, and it has a value of 6.63 times 10 to the minus 34. So Planck's constant, there is a proportional relationship between energy and frequency. And the threshold frequency for a particular metal is given as F subscript 0, which is equal to E over H. We can also talk about the threshold wavelength, or we might want to convert to the wavelength, for example. And we know that the speed of light is equal to the wavelength multiplied by the frequency, and therefore we can put that into this equation here, substitute it in by knowing that the frequency is c over lambda, and therefore this equation, E equals hf, becomes hc over lambda, and the threshold wavelength then becomes hc over the energy. So the most important relationships are this one and an understanding of the threshold frequency. So for this situation up here, we have the metal and the electrons at the surface. We have the incoming photons, these particles of light, and they are being absorbed by the electrons, and the electrons cannot escape. It's not enough energy. So what happens is that the energy that they have collected is dissipated to the surrounding material, and the electron stays where it is. In this diagram here, we have photoelectrons being released. And that's because the electron at the surface of the metal is absorbing higher energy photons. The photon is being absorbed by the electron, and the electron is able to escape the metal. Remember that it is one photon being absorbed by one electron. So in this situation, at the threshold frequency, the energy of the photon at the threshold frequency is the energy that's absorbed by the electron. When we are at the threshold frequency, that amount of energy is known as the work function. And the work function is different for every different type of metal. So it is dependent upon the metal. A zinc plate, a platinum plate, they will have different work functions and therefore different threshold frequencies. Once the electron in the surface of the metal, once it has absorbed the energy from the photon, it will escape. It will escape and it will have no energy left over. So the kinetic energy will be 0. And that's because it used all of the energy from the photon to escape the metal, and there was none left over, which is unlike the next situation where the frequency of the light is greater than the threshold frequency. And that means that the energy that's absorbed is greater than the work function. The energy that's absorbed is equal to the frequency of the light, and in this situation the frequency of the light is bigger than the threshold. So the energy is bigger than the work function. And in this situation we have electrons at the surface and electrons deeper down. The photon being absorbed is very high energy. Electrons at the surface can escape with quite a high kinetic energy, and the ones in the surface absorb, the ones deeper below the surface absorb the photon. They need to use some of that energy to escape through the metal, but once they get to the surface, they just need the work function to escape further, and they're able to escape as well, but with a smaller kinetic energy. The kinetic energy for the electrons in the surface is the maximum. So kinetic energy max. And the frequency and the energy and the work function are related with this equation. The energy in the photon, which is equal to hf, is equal to the work function plus the maximum kinetic energy. This is the energy that's delivered. This is the work function that needs to be used to escape the surface. Anything that's left goes to kinetic energy. And notice that we're talking about the maximum kinetic energy, which is what we get for electrons at the surface only. When you're at the surface, you don't need to use any energy to escape through the metal itself. You're not buried deep inside and have to climb your way out. You're already at the surface, and all of the leftover energy goes to kinetic energy. These photoelectrons are going to have an energy, a kinetic energy, that is smaller than those that were at the surface. So what you end up with is you have electrons that were at the surface escaping with a very large velocity, and electrons that were deeper down escaping with a smaller velocity. This is the main equation that you'll want to be taking away from this video. I'm now going to make a small note about the historical context of this discovery. Albert Einstein and Mileva Maric were a married couple in the early 1900s. They were both physics students together, and she was in the middle of a PhD. He had a job at a patent office doing an administrative job. They worked together on physics theories, and she helped him a lot with the mathematics. In 1905, he published 4 papers. This is known as his Annus Mirabilis, or Miracle Year. The Annus Mirabilis papers included the photoelectric effect, the concept of Brownian motion, special relativity, and the equation E equals mc squared. All of these were published in the same year, in 1905. And it's widely accepted that his wife helped him with this and that it was a joint endeavour. Later, in 1921, Albert Einstein was given the Nobel Prize for Physics for his work on the photoelectric effect. By this time, he and his wife Maliva were divorced, and she was raising their children. It's worth noting that the money that he was awarded for winning the Nobel Prize, he donated in its entirety to Maliva. How much she helped him, nobody will really know, and that information is lost to history. But Albert Einstein is remembered for being one of the great minds of the 20th century, and Maliva has largely been forgotten.